Welcome back to my second part of proof by induction. There, that sounds a lot better. So of course if you haven't yet, check out the first video. I go over some of the basic setup for the notion of proof by induction, and I go through a couple of more basic examples. So I left off with a cliffhanger, or homework assignment, however you want to think about it, that I had a couple of problems that I wanted you guys to try and work on. So my first example was show that the sum of the first n odd positive whole numbers is equal to n squared. The second one being that the sum of the squares of the first n positive integers, or whole numbers, however you want to think about it, can go by n times n plus 1 times 2n plus 1, all divided by 6? Really? That seems weird. So, of course, we talked about our methods of going through the notion of proof by induction. So we have our three basic steps, of course. Step 1, prove it is true for a trivial case. Step 2, assume it to be true, and then step 3, prove it works on the next iteration as well, assuming what you believe to be true is still holds. So let's look at that example for number 1. We wanted to see if the sum of the first n odd positive integers, so that would be like 1 plus 3 plus 5 plus 7 plus 9, going as far as we want to see in fact if that sum is n squared. And in fact, in the n equals 1 case, this is pretty obvious, straightforward. It's like 1 squared is 1, so 1 is 1. Done. Well, that's good. Step 2 is to assume that this holds true for the first k, or whatever number you want to plug in there, odd positive integer. So again, like we mentioned, 1 plus 3 plus 5 plus 7, etc., etc. What we're going to want to do in this case is try and find some way to express the kth odd positive integer. So in fact, if we go by the formula 2k minus 1, where k is that number of that number of integer, then that will give us, in fact, the kth odd integer. So if k was 1, then we get 1. If k is 2, then we get 3. If k is 3, we get 5. So again, note that it's just going up by 2, as we would expect it. So we can express our sum in this fashion, or if you know summation notation, we can use this formula that we have here on the left. So of course, we assume that this is true for the integers 1 through k, or for the first up to the kth odd positive integer. We want to prove that this is in fact k squared. So we need to see if this holds for the next case. So then the sum of the first k plus 1 odd positive integers should in fact be k plus 1, that whole thing squared. So let's see if that is in fact what happens here. So of course, like we've done in our previous examples, we can break up the sum of the first k plus 1 integers, or k terms in this case. We can break that up as the sum of the first k plus the very new one that we've just added. And of course, by our assumption, we already know that this part can just be expressed by k squared. So of course, now we need to add our new term to this series. So we can literally just plug in k plus 1 into our formula. So of course, after we clean this up a little bit, it will become 2k plus 1. So in fact, the sum of all of our integers is now k squared plus 2k plus 1. Well, isn't that k plus 1 quantity squared? It is. So in fact, we have shown that that what our assumption holds true for the next case, and so by our proof of induction, we are done. So we have now shown that the sum of the first n odd positive integers is in fact n squared, whatever that number happens to be. Let's quickly look at our second example. So we want to prove that the sum of the first n squared numbers, so 1 squared plus 2 squared plus 3 squared plus 4 squared, so that's 1 plus 4 plus 9 plus 16, that we can actually express that sum by this weird looking formula over here. I admit, it does look pretty weird. So the fact is, testing it for our n equals 1 case, we just plug in 1 for n, everything through. The 1 squared is still just 1. And in fact, if you plug in n equals 1 to the formula, you get 6 in the numerator, 6 in the denominator, and you are good. So of course, we now assume that this holds true up to case k, so that the sum of the first k squared positive integers is given by the formula as we've seen it before. We just have k here instead of n. So now we need to see if this is going to hold true for the very next case up, for the sum of the first k plus 1 squares of numbers. So by plugging in k plus 1 here, in place of each of where we had k originally, we need to see if in fact our new sum can be written as k plus 1 times k plus 2 times 2k plus 3. So again, I just plugged in k plus 1 here, and then I distributed everything through. So that's where the 2k plus 3 term came from. So let's see if, after we do a little bit of algebra, see if this thing actually pops out. So like we've seen before, we can actually break this up into the sum of the first k squared numbers plus our very last one. So of course, by our assumption, our first sum of the first k squared numbers is, as we were seen before, our formula. And of course, we're just adding our newest term at the very end. So I did this one way through factoring out. Notice that each part has a k plus 1 term. So I factored that sucker out, and then I saw what I had left over. So from factoring, we have k times 2k plus 1 over 6 on the left, and then another factor of k plus 1 on the right. So of course we have a fraction and a not a fraction, so easiest way to combine these things is to make everything a fraction with the same denominator. So k plus 1, I just multiplied both the numerator and denominator by 6. So this fraction is now 6k plus 6, all divided by 6. So that's good. So now we in fact have everything under one common denominator. We can just combine these terms up. We have 2k squared plus k plus 6k plus another one. So that becomes 2k squared plus 7k plus 6 all over 6. And of course that whole thing is still multiplied by k plus 1. Well, if you guys remember how to factor quadratic polynomials, in fact, you can factor 2k squared plus 7k plus 6 as k plus 2, 2k plus 3, which is what we wanted to prove in the first place. So in fact, yes, the proof by induction formula does work for our next case as well. So we have in fact proven that for all positive integers, that the sum of the first n the sum of the first n squared numbers is in fact as we had expected.